Hey everyone, ready for another deep dive? Today, we're going to be tackling a concept you might remember from your high school physics class, gravitational potential energy.
Oh, yeah. That takes me back.
But we're going to go a little deeper than that classic formula, PE equals mgh.
Right, we're going to be exploring how this energy really plays out, like across the whole universe.
Exactly. And to help us do that, we're turning to a fantastic resource, a page from Open Educational Resources Open Source Physics at Singapore.
They explain it all so clearly, and they even have an interactive simulation for us to play with.
Awesome. I'm a hands-on learner, so I'm looking forward to that. Okay, so let's start with that familiar formula, PE equals mgh, mass times gravity times height.
Yeah, that's the one most people learn.
But I have a feeling there's a lot more to this story, right?
You're absolutely right. It's a good starting point, but, it's really a simplification.
Oh,
Yeah, it works well for objects that are near Earth's surface, where gravity is pretty constant. But think about it, like what happens when a rocket launches into space? Things get a little more complicated, I imagine.
oh yeah, way more complex. So to really understand that, we need to bring in the universal formula.
Okay, let's hear it.
Here it is, drum roll please. U equals negative GMm over R.
Oh, wow. That looks a little intimidating.
I know, it might
Yeah.
seem like a mouthful, but trust me, it's not as scary as it looks. Let's break it down together.
Okay, I'm ready.
Okay, so U stands for gravitational potential energy.
Got it. And that's what we're trying to figure out.
Exactly. Then we have G, which represents the universal gravitational constant.
Ah, gravity. That makes sense.
And this constant basically tells us how strong gravity is between any two objects in the universe.
Wow, so it's a universal constant, so it applies everywhere.
Exactly.
Cool. Okay, what about M and M?
Good question. M is the mass of the larger object. So in our rocket example, that would be Earth.
Right, and M is the rocket.
You got it. M represents the mass of the smaller object.
Okay, so we've got the masses, we've got the gravitational constant.
Hmm?
What's that R doing down there?
R is all about distance. It stands for the distance between the centers of those two objects.
Oh, I see. So between the center of the Earth and the center of the rocket.
Exactly.
So this formula takes into account how the force of gravity weakens as the distance between those objects grows.
Exactly, like as our rocket moves further away from Earth.
Okay, so the universal formula gives us a more complete picture then.
Way more complete. It lets us see how gravity really works across different distances, not just near the surface of the Earth.
This is already making me think about potential energy differently, but there's one thing about that formula that's really throwing me off.
What's that?
That negative sign. Negative energy. What's that all about?
Great question. It all comes down to how we actually define potential energy.
Okay.
It's always measured relative to a specific reference point,
A reference point.
right? Like a starting point. And in the case of gravitational potential energy, that reference point is set at an infinite distance from the source of gravity.
Infinite distance. So like really, really far away from Earth.
As far away as you can possibly imagine. So any object that's bound by Earth's gravity, it's going to have negative potential energy.
So it's not that the energy itself is actually negative, it's more about its position compared to that infinitely far away point.
You got it. It's kind of like thinking about elevation. We say a valley has a negative elevation compared to sea level.
Oh, right.
Even though that valley is obviously still above the Earth's core, it's all about perspective.
That makes a lot more sense. So negative potential energy just means that an object is like trapped by a gravitational field.
Exactly. And it needs energy to escape that field.
Just like our rocket needs a ton of energy to overcome that negative potential energy and break free from Earth's gravity.
Precisely. And to really grasp this idea, we need to delve into the formal definition of gravitational potential energy.
Okay, hit me with it. What's the official definition?
Well, according to the website, it's defined as the work done by an external agent to bring a mass from infinity to a certain distance from the source mass. Think of it like when you're pulling a magnet off your fridge.
Oh,
That effort you're putting in to pull that magnet away, that's kind of like the work done to bring a mass from infinity.
so the closer an object is to a source of gravity, the lower its potential energy because it took more work to bring it there from that infinitely far away reference point.
You got it. It's like rolling a ball uphill. You know? The higher you go, the more work you put in, and the more potential energy the ball has at the top.
That makes sense. And speaking of getting hands-on, I hear the website also has a cool interactive activity to help us visualize all of this.
They do. I'm excited for us to try it out.
Me too. Let's dive into that simulation next.
Okay, so this simulation shows a green test mass.
Right.
and it's starting 100 meters away from this source mass. We're supposed to note the potential energy at this distance. Looks like it's negative 6.67 times 10 to the negative 11th joules.
Okay, good. Now try moving that test mass closer to the source, and let's see what happens to the potential energy value. What do you notice happening?
All right, let me try moving it to 50 meters. Whoa, okay, the potential energy got more negative. Did it?
Yeah, it's now negative 13.35 times 10 to the negative 11th joules.
Mm-hmm.
It's kind of like that magnet analogy you were talking about earlier.
Uh-huh.
The closer the magnet gets to the fridge, the harder it is to pull away, so it has lower potential energy.
You got it. That's a great observation. And the simulation is basically showing us that same principle, but, with gravity.
Right.
As that test mass gets closer and closer, the potential energy decreases. It gets more and more negative.
Okay, so now the website is asking us to calculate the change in potential energy between 100 meters and 50 meters.
Okay.
And they even provided the calculation for us using that universal formula.
Oh, I see.
Yeah, so this calculation is basically showing us the difference in energy that's needed to bring that test mass from infinity to those 2 points, 100 meters and 50 meters.
Okay.
It's about negative 6.67 times 10 to the negative 9th joules.
So we're not just thinking about that potential energy at like one single point,
Yeah.
but we're also looking at how it changes as the object moves around.
Exactly, yeah. As it moves within that gravitational field. Okay, cool. Now they're giving us this equation, negative 6.67 times 1 times 100, divided by the absolute value of r.
All right.
We're supposed to plug this into the simulation. What is that going to show us?
Exactly. Try plugging that equation into your model section and see what happens.
Okay, give me just a sec. All right, I think I got it. Oh, wow, I see it.
What do you see?
A teal line just popped up on the graph, and it says it represents the predicted potential energy values that are based on this model.
Right.
And wait, it's lining up perfectly with the orange line.
Nice.
The orange line is the actual potential energy from the simulation.
Right.
That's crazy. The model predicted the results, perfectly.
I know, it's amazing. It really shows you how powerful that universal formula is,
Right.
like how well it captures how gravitational potential energy actually works.
Right.
When we use the right values for this specific situation, we can get super precise predictions.
This whole deep dive has been a real eye-opener. We started with that basic formula, then we dug deeper into this more universal equation, and now we're even testing things out with these simulations.
That's awesome, right?
Yeah. And what I really like is that this website makes all these concepts super accessible. It makes it fun to learn and encourages us to just try things out.
Right. It's all about exploring and experimenting.
Yeah.
But before we totally wrap things up, I want to leave you with something to think about.
Oh, okay. I'm listening.
So think about how this idea of gravitational potential energy, how it actually plays out in other parts of the universe. Imagine the planets orbiting the sun.
Okay. Yeah, I'm picturing it.
So if a planet is closer to the sun, it has, lower gravitational potential energy.
Okay.
And that means it took more work to bring it to that spot from, infinitely far away.
Okay. Yeah, that makes sense.
But remember, energy doesn't just disappear. It transforms. So that lower potential energy gets converted into another type of energy, kinetic energy.
Kinetic energy, the energy of motion. So a planet that's closer to the sun, it's moving faster.
Exactly. And then on the other hand, when a planet is farther from the sun, it has higher potential energy.
Oh, okay.
And lower kinetic energy, so it orbits slower.
So it's like that ball rolling down a hill.
Yeah.
It speeds up as it gets closer to the bottom because its potential energy is turning into kinetic energy.
Exactly. You got it. And that interplay, between gravitational potential energy and kinetic energy, that's what shapes those elegant orbits we see. Those elliptical paths the planets take around the sun.
Wow.
But it doesn't stop there.
Oh.
This same principle applies to things that are even smaller, like crazy small.
Like what?
Like electrons in an atom.
Wait, really? Electrons orbiting the nucleus of an atom?
Yeah. Now, the analogy isn't perfect, but it's still helpful to think about electrons as being bound to the nucleus by an electrostatic force.
Yeah.
And that force, it kind of works similar to the gravitational force between, a planet and the sun.
So an electron that's closer to the nucleus, it has lower potential energy. Because that's like a planet that's closer to the sun. And that means it has higher kinetic energy. That's incredible. This one concept, potential energy, it applies from planets to atoms.
I know, right? It's amazing.
Yeah.
And understanding this is key to explaining how atoms actually absorb and emit light.
Whoa. So we've basically gone from a physics classroom to outer space, and now down to the tiniest level, all thanks to this one idea.
It is pretty wild. It just shows you how fundamental this concept of potential energy really is.
Totally. Welcome back to the deep dive. Before we wrap up our exploration of gravitational potential energy, I'd love to hear a little bit more about how this concept applies to electrons in an atom.
Yeah, sure.
It's amazing how we've gone from rockets to planets and now down to the subatomic level, all thanks to this one idea.
Yeah, it really highlights the interconnectedness of physics, doesn't it?
Yeah.
But remember, when we talk about electrons orbiting the nucleus, we're using an analogy.
Right.
It's not exactly like planets going around the sun,
Right.
but the core concept of potential energy still applies.
So remind me, how does it work with electrons?
So picture an electron hanging out near the nucleus of an atom.
Okay.
Now, because it's attracted to that positively charged nucleus, opposites attract,
Mm-hmm.
it has lower potential energy when it's closer.
Okay.
And just like what we talked about with the planets and the sun, that lower potential energy means higher kinetic energy.
So the closer an electron is to the nucleus, the faster it's moving.
Exactly. And the farther away it is, the higher its potential energy and the slower it's moving.
Okay.
Now, this might seem a little abstract, but it has really huge implications for how atoms behave.
Oh, like what?
Well, it explains why atoms absorb and emit light at very specific wavelengths.
Huh?
So when an atom absorbs energy, say from a photon of light, its electrons can jump to higher energy levels, further away from the nucleus.
It's like climbing an energy ladder.
That's a great way to put it. And then when those electrons fall back down to lower energy levels closer to the nucleus, they release energy in the form of light.
So the colors that we see in fireworks or neon signs, that's all thanks to the interplay of potential and kinetic energy at the atomic level?
It plays a big part, yeah. It's incredible how this one seemingly simple concept we've been talking about has such profound effects on, the world around us.
I know, this whole deep dive has been a real mind bender in a good way. We learned about the limitations of that, classic MGH formula, explored the more universal equation, and now we've uncovered how gravitational potential energy is at play in everything from rocket launches to planetary orbits, even to the behavior of atoms.
It's amazing, right? It just shows you the power of physics to explain the universe, from the very large to the incredibly small. And it's a reminder that there's always more to learn, always more to discover.
Absolutely. I feel like I have a whole new appreciation for this fundamental force that, like, shapes our reality.
I'm glad to hear that.
A huge thanks to you for guiding us through this fascinating exploration.
It's been a pleasure.
And to all of you listeners out there, keep that curiosity burning.
Yeah, there's a whole universe out there waiting to be explored.
We'll be back soon with another deep dive. Until then, keep exploring and don't be afraid to question everything.